Hello everyone, welcome to the channel of Algocamp. So in this particular series, we are going to start talking about a few interesting concepts around data structures and algorithms. These videos are going to be power packed with in-depth explanations, problem solving around some very important aspects of data structures and algorithms. DSA is one of the most important topics when you see software engineering interviews for both internships roles and full-time roles. And I see that a lot of people actually struggle with that. So in this particular video series, what I have tried is I have tried to make sure that I try to solve the problems and try to explain the corresponding concepts with a more intuition building kind of like a scene. And we will be doing a lot of pattern based problem solving so that you can actually see what kind of problems can be solved with a specific type of algorithmic pattern. In this particular start of the series, we are going to actually start with searching algorithms. I believe searching algorithms are one of the most important algorithms if you want to actually excel in DSA, and a lot of advanced concepts in DSA do rely on searching algorithms. So without any further ado, let's just start this particular video, but I would highly encourage you to do subscribe to the channel if you have not yet subscribed, because we are going to put some really awesome content coming up ahead, and all of these videos are going to be really helpful for you for preparing for your next software engineering interviews. So let's just start. Also, if you are somebody who is actually willing to prepare for software engineering interviews and want a more structured curriculum around high-level design, low-level design, other aspects of interview preparation around system design, or you are more interested in around learning back-end development concepts with Node.js, Spring Boot and whatnot, then do check out the website of algocamp.io. Here we have tons and tons of live courses where we talk about some really interesting concepts around software engineering. So do check out the website and start preparing for your software engineering career, because all of the concepts that we are going to talk about are one of the most important ones to become a better engineer and also to actually crack all the software engineering interviews. So let's come back to the video. So in computer science, there are a lot of problems that have some very good amount of solutions already built up, and some of the problems are still getting figured out, right? Among those, there is a problem called as the problem of searching. Now, searching is not a new problem that we have to figure out a new algorithm or research on a new algorithm, because searching is such a fundamental problem in computer science that you will find ample amount of algorithmic discussions already being done regarding searching. Searching as an exercise you can see, or as a problem you can see on different applications that you yourself use in your daily life. For example, if you open an e-commerce, then inside an e-commerce you are able to see kind of like a search bar on which you can search for a product, right? Whereas if you go on any OTT platform like Hotstar or Netflix, then you actually see a search bar using which you can search for some movies, right? So searching is like everywhere. Almost most of the mobile applications that you see have some element of searching. For example, even in your contacts app, right? Even in your contacts app, you have a searching mechanism using which you can search for contacts, right? And everywhere this thing works separate, like in a different way. Everywhere this thing works in a different way. For example, if I talk about searching in a contact list, then generally, like, this implementation can vary device to device and OS to OS, but generally when we type SA, then your contact list suggests you all the names starting with SA: Sanket, Samir, Sarthak, right? All of the names it starts you suggesting. So this kind of a searching where you search based on prefix, where the prefix should be SA, is called as prefix searching, right? Different type of searching exist, and to be very honest, for searching different kind of data or solving different kind of searching problems, we have different algorithms already with us, right? Based on the problem in hand, we will try to figure out some algorithm or some data structure that can help us in searching, right? This is something that we have to keep in mind. Now, having said that we have searching as a problem with us, in this, I would say, module, we are going to talk about 2-3 basic searching algorithms that can help you to solve the most basic searching problem. That is, if you have a set of data and you want to find some data, How can you find that? Simple searching. Slowly and steadily, when you will learn more data structures, more algorithms, more complex cases, then you will realize that there are more situations in which technique of searching is used, but maybe with an amalgam of another data structure or with an absolutely different strategy at all, right? And you then enhance over the problem of searching, right? So we are going to mainly talk about this problem of searching, some basic algorithms, and the problem solving around those algorithms that we are going to learn in searching. So I hope the basic crux about what the problem of searching is and why we are actually learning it is clear to everyone. So let's start with a problem statement in hand and try to figure out what can be done, right? So the problem says that you have been given an array of numbers and a target value x. Okay, you have been given an array of numbers and a target value x. You have to check if x exists in the array or not, right? So you will be given an array, and this array is not arranged in any specific order. No property you can like directly decipher here. It's like a random array, right? And you have an element x that has been given as the input to you. You have to check if x exists in the array or not. You have to figure out whether the element x is existing in the array or not, right? If the element x exists in the array, then return index of x if it exists, else return -1. So if you are able to successfully find x inside the array, you should return the index of the element x, that at what index you found that element, right? And if the element is not found, then you can return -1. Here you can avoid considering the cases that what if the element is present more than once or something, because in that case you can assume any index you can return. So for the timing, for the sake of simplicity, we are going to consider that every element is present, let's say once. Okay. And then we have to figure out at what index x is actually present. This is the problem statement in hand. Okay. Now, first of all, in order to solve this problem, let's try to figure out a brute force solution. Okay, and this brute force solution is going to be kind of very important because it will lay the foundation of the first algorithm that we have to understand. So if this is the given array, let me just copy this from here. If this is the given array, then can I say that our element x that we have to find might be present on any index? We are not sure. And in the worst case, what can even happen that x is not even present anywhere in the array, right? It's not even present anywhere in the array. Basic case can be it is present. In the worst case, it can occur that x is not even present in the array, right? So how can you figure out? So we don't know at what index x is there, right? I don't know. But maybe, just maybe, if we can go at every index of the array, right? I can explore every index of the array one by one and explore that whether at that particular index do we have x or not? Do we have x or not? And if we are able to find x on that particular index, then we can return that index. Let's say this index will be having x. Otherwise, if we explored all the indexes, and still we are not able to find x, then we can say x is not even present. And you might be thinking that how I came up with this brute force solution. Just think about it. No, if x is expected to be found inside an array, then I cannot check it without knowing what is present in the array, right? So let me write it. If x is expected to be found in our given array, then we can't decide this without knowing the content of the array, without knowing content of the array, right? if you have not read the content of the array, you won't be able to judge whether X is present there or not. Why? Because this array is not possessing any specific property. It's like just a random array. There is no correlation between the elements or the arrangement of elements. That's why I'm saying if you want to just check whether X is present or not, then bare minimum, you have to at least read the content of the array, right? That's what I'm doing. I will keep an index I, and one by one, I will go to every index and check whether this element I, element pointed by I, is equal to X or not. So we'll see. What is the element at index I? 9. Is 9 equal to X? No. So if 9 is not equal to X, then I will move forward. Is the element pointed by index I is 3. Is 3 equal to X? No. I is now pointing to 1. Is 1 equal to X? No. I is now pointing to 10. Is 10 equal to X? No. And so on. And so on. Right? We'll just move our variable I one by one to all of these indexes. And when we reach an index where the element at that index is equals to X, I found my answer, and my answer is the current index I. Can I say that? So if I have to implement this algorithm, I can say for I equals to 0, right? I less than n, assuming n is the length of the array, I plus plus, we can say that if array at I, that is the current element present at the ith index in the array, is equals to X, that is the element that we are trying to find, we are going to immediately return I. And if we never return from this for loop, we are going to return -1, because let's talk about it. If you never found the element, let's say you are iterating over every index and then checking whether the current element is equal to X or not, and you exhausted all the indexes, in that case, you never found this element, right? Then you are going to return -1. I'm assuming you will be binding this whole code inside a function, right? So what is actually going on here? What is actually going on here? Let's take this discussion to a more technical term, right? Can I say that when we were given the problem, this thing, the thing that I'm going to talk about is going to be problem to problem dependent. When I was given the problem, then I can say that our element X was expected to be found among these elements only, right? I don't need to check anywhere else to find X, right? Based on the problem, I am sure that if we have to find X, we have to find it in these given set of elements only. We don't need to go somewhere else or do something else. If X is expected to be found, it is expected to be found inside the array only. Can I say that? Right? It's not like an infinite, or I would say universal search that we have to do everywhere sometime, right? You are bounded, that you have been given some elements. Within these elements only, try to find X. Can I say that? So our search space, so there is a term called as search space. Okay. There is a term called as search space. In easy words, what do you mean by search space? Search space means the collection of data among which we have to apply our searching algorithm, right? The collection of data in which we have to apply our searching algorithm. For example, here the collection of data are the elements from this array. So this array becomes our search space, or I can say these elements becomes our search space, because the data pointers among which we have to do the searching are these data pointers only, right? So we can define search space as collection of data where searching is expected to be done. Now fun fact. Now in this example, you are able to see that there was an array. Inside that array, there were some set of elements. And among those elements only we expect X to come, right? But there can be a case that You are, let's say, given a range. Instead of an array, you are given a range. For example, 1 to some value x. And within this range, we have to apply our searching algorithm. Then I know whatever I'm searching for is present inside this range. Can I say that? For example, let's say you expect me to find the third multiple of 7 inside the range 1 to x. Now I know whatever is the value of x, based on that, there is an element which is the third multiple of 7, right? There's an element which is the third multiple of 7, that is 21, right? We are technically trying to find 21 in the range 1 to x, that whether 21 exists in the range 1 to x or not. Now this range is not an array, right? This is just a range. I'll just explain it like low and high, that low was 1, high was x. So this is just a range. This is not an array, but we are still trying to apply some searching algorithm there, right? So this also qualifies for a search space, although this is not an array. So this is something that we need to write. It doesn't always need to be array, right? Search space always doesn't need to be array. It can be something like a range or something else, right? Something else. So searching can be done on a search space, right? This is the basic definition of search space, and this was a basic brute force algorithm that we deciphered. Now let's talk a bit more about this brute force algorithm with respect to our search space, and then we will be able to concretely give it a name, or I would say give it a special significance altogether. Now we know that there is a concept of search space, right? So technically, if I say that I wanted to search x, this array was of length n, right? Let's say the array length was n. Then can I say when we started looking for x, this search space was of size n, right? When we started looking for x, size of search space was n, right? Size of the search space was n. Why? Because the data or the collection of data among which we have to search for x are n elements, n data pointers are there. Then I compared the element at I with x, that is my 0th index element. This is my 0th index element. I compared my 0th index element with x and found that this element is not equal to x. So what will I do? I will discard this element because now we don't need this element, and I will move I forward. Now technically what just happened was, in this iteration, we reduced the size of the search space from n to n minus 1. See, initially we were having all n elements, then you rejected this element, so you are left with n minus 1 elements inside which you are going to search for x, right? So after every iteration, we reduce size of search space by 1. See what is going on? Now you will compare 3 with x. Now 3 is also not equal to 13, right? So what you're going to do, you're going to move I ahead. Now this is also now removed from the search space, and now your search space is left with n minus 2 elements. Previously it was n, then it went to n minus 1, then it will be going to n minus 2. Then again, is 1 equal to x? No. So I'll avoid this element also, and now 1 is also rejected. So technically now 3 elements are gone. You are left with n minus 3 elements. Can I say that? So this goes to n minus 3 elements, and so on and so on, right? So technically what is going on, initially your size of the search space was n, then after one iteration your size of the search space became n minus 1 because you discarded one element. Then the size of the search space became n minus 2 because you discarded another element. Then the size of the search space became n minus 3 because you discarded another element, and so on. At last, finally, you can say that you are going to exhaust the size of the search space, and it is going to become something like equal to 1 or 0, right? That you are just left with the final element. You're just left with the final element 2, right? So let me draw it here. Okay, and then you check whether 2 is equal to x or not, and so on. This is considering that x was not even present in the array. Let's say x was 33. So x is not even present anywhere in the array, right? Then you will compare it with 2. Is 2 equal to 33? No. And then move forward. And even this one size search space will reduce to 0, right? So this is going to be the worst case. When element is not present. Okay. This is the worst case, when the element is not present. And you can see in this case, every time we are reducing our search space by 1, our search space by 1, our search space by 1, so on and so forth. Finally, our search space by 1. And at last, you reduce your search space so that there is nothing left to be searched. Right? So we can say that we are linearly reducing the search space. Right? We are linearly reducing the search space size in every iteration. That is why this brute force is called as, this is why this brute force algorithm is called as linear search. Right? What is linear search? In linear search, you have a set of data. That set of data gives you a search space. You try to reduce your search space size every time by 1 by checking whether the current element is equal to your target or not. If the element is not equal to the target, you reduce the search space size by 1. Right? This is the simple definition of linear search. And this is the simple coding implementation of linear search, that all you have to do, start from the 0th index, go till the last index. Every time just check an element, whether it is equal to the target x or not. If it is, then all you have to do is just return the index. But if no element was equal to x, then this loop will end. And at last you are going to return -1. As simple as that. So this was linear search for you guys. And I hope this basic algorithm of linear search, where we are searching an element inside an array with no particular order or no arrangement at all, is clear to everyone. Now we learned about an algorithm in which we were not putting any brain, kind of like brute force. We go to every element one by one and reduce the search space. Now technically, if somehow search space possess a few particular properties, then we can optimize the solution. Right? We can do something better than order of n if somehow the search space possess a few particular properties. Okay. So what do we say is that, let's say this is our search space. This is our search space. Okay. This is the lowest point of the search space. This is the highest. So we can say low to high actually represents the search space. Now this low to high can be indexes of the array also, or it can be starting and ending point of a range also. Anything can be there. But I'm saying that, let's say you have a search space of this size. Now what you can do is you can divide your search space into two halves. You can divide the search space into two halves, right? Considering divide the space in two halves, considering that both halves are different from each other based on a property, based on some properties. Right. So what we are trying to do here is we will try to divide our search space into two halves, right? Depending on a condition that both of the halves should be different than each other based on some property. Based on some property, they should possess some different, I would say, identities, or they should possess some different properties. If that is the case, then we can divide our search space into two halves. We can discard one half based on those properties that we just thought of. We can discard one half and we can accept one half, right? Whatever half is discarded, we are going to forget it. And then on the remaining half, let me write it like this here. On the remaining half, this is the remaining half. On the remaining half, we repeat the process. Repeat on remaining half, right? In this way, what is happening? Instead of linearly decreasing my search space, I decreased my search space from n to n by 2, right? Because I reduced everything such that half of the search space is gone in once. In linear search, only one element was gone in one iteration. Here, half of the elements are gone in one iteration. Then you will repeat the process. You will again divide the array or divide the search space into two halves. You will discard one half, you will keep one half. And then again, you are going to discard half of the elements. So the search space will be left of size n by 4, because on the half of the search space, you again halved it. So you will be reducing to n by 4 and so on, right? And how we are doing this? Just based on the fact that if you divide your array into two halves, or you divide your search space into two halves, then both of the halves should be different than each other based on some property. If all of these conditions satisfy, then you have given birth to a new algorithm called as binary search, right? Binary search. Now on the internet, if you will go, a lot of people will say that if the array was randomly arranged, then you can apply linear search. But if the array is arranged in sorted order, then you can apply binary search. You will find this statement a lot of people saying that if the array is sorted, then only you can apply binary search. This is not completely true. In order to apply binary search, you don't need to have a sorted search space always. You don't need to have a sorted search space always, right? Instead, what you need to have is a search space. If you divide it into two parts, then one part differs from the other part based on some property. If this exists, then you can apply binary search. So nowhere in your life, I at least assume that after this lecture, you will say that binary search can only be applied on sorted arrays. No, technically not. Binary search can be applied on unsorted situations also, but the search space should possess the property that if you divide it, then both of the halves will be different in some manner. If the search space possesses this property, then still you can apply binary search. Now you might be thinking, how will we identify the property and all? So don't worry. Based on our problem solving, we are trying to, I would say, understand binary search in as in-depth manner as possible. We'll do ample amount of problem solving so that it gets clearer and better in your head that how to apply binary search. But I hope the basic idea about what binary search is and like how it actually approaches a problem by dividing the problem into two halves, discarding one half, accepting one half, is clear to everyone. So we have a new problem in front of us. Problem number 704, binary search. Name of the problem is binary search itself. Easy problem. I would also say it as easy problem. More than 7,900 upwards, close to 8,000. You can see few companies it has been asked in because it's a very basic problem and it actually helps us to understand binary search well, right? So the problem says that you have been given an array of integers nums. So you have an array of integers nums which is sorted in ascending order. So whatever is the array given to you, that array has been arranged in ascending order already. Okay. And an integer target is also given. So apart from the ascending order arranged array, you also will be given a target. Write a function to search target in nums. So you have to write a function such that you are able to search target, the value that is given to you inside the array nums. If target exists, then return its index. So if you are able to find target in the array, you have to return the index. Otherwise, return -1. So if you are not able to find anything in the array, you have to return -1. You must write an algorithm with order of log n runtime complexity. Don't worry, we'll come to it. We'll come to it. But this is the basic problem in hand. You can see the array nums. It is arranged in ascending order. This is the target, and we are able to find 9 on 4th index, whereas we are not able to find anything as 2, so the answer is -1. Okay. Length of the array for the time being is given as 10 is per 4. Okay. So this is the problem in hand. Now, the situation is that a lot of people explain binary search using this problem because this is one of the easiest problem that you can solve using binary search. But please don't keep the notion that binary search can only be applied in ascending order situation or a sorted situation. We have situations in which binary search can be applied even when the array is not sorted, right? Or the search space, let's not talk in terms of array, the search space is not sorted, still we will be able to apply binary search. It just depends on the condition, right? So let's talk about that condition, explore that condition a bit more, see how we can divide the array here, or we can divide the search space here such that one half of the search space is different than the other half of the search space, and how we can discard one, how we can accept one. Let's talk about it. Now we have been given this array. You can see the array is arranged in ascending order. Within this array, we have to find this target. So first of all, if I try to define my search space, then I can say that the array of size n is our search space. Okay, the array of size n is our search space. So if I define the starting of the search space, this is low and this is high. Low denotes start of search space and high denotes end of search space. Okay, cool. Now, what did we understood in the basic definition of binary search? We understood that we try to divide our search space into two halves. Okay, let's try to divide it. So if I want to divide my whole array into two halves, let's get the middle element. So middle element we can get from low plus high by 2 for the time being. So 16 plus 0 by 2 is 8. So 8 becomes our middle element. Okay. Now I need to figure out a property based on which one half of the search space is different than the other half of the search space. Let's try to figure out that property. Okay. So property number 1. If the element that is pointed by mid, if ARR of mid, if this element is less than the target, then can I say that? Can I say that if this element is less than the target and this whole array is arranged in ascending order, then to the left of this element, all of these, right? All of these elements are less than 23 itself, and 23 is less than 37 itself. So can I say this whole range from low to mid is less than 37. Can I say that? Right. I'm saying that if 23 is less than 37, this whole array is sorted, then on all of these elements are less than 23, then all of these elements will be less than 37 also. Now just think about it. One half, that is the left half. In the left half, I can see all the elements are less than target. All the elements of left half is less than target. Whereas, if you see the right half, this is your right half. This is your right half. In the right half, some elements might be less than 37, some might be more than 37, or some might be equal to 37. We cannot have any distinguished arrangement here. Some are less than 37, some are equal to 37, some are more than 37. So I can say that this is a property based on which both of the halves are differing, right? That one half is all less than 37, no doubt at all, but the other half maybe or maybe not. So what we can do, here I can apply binary search. So what does binary search says? Because the search space has two different properties on both the ends, what we can do, we can take a decision to discard one half of the search space and take one half of the search space. So let's see, if 23 is less than 37 and everything to the left of 23 is also less than 37, then I can never find 37 here, because in this left range everything less than 37 exists and 37 is greater than all of these elements. So I can say that I don't need this left region. This whole left region can be discarded, and then this right region is something that we need to still explore. We are not sure about this right region, but we are damn sure about the left region that it will not be having our target. So if this is the case, then we can say discard left half. If you're discarding left half, of course you're taking the right half. How do you discard the left half? Now low denotes start of the search space, right? If you have to discard this region and keep this as the search space, 29 becomes the start of the search space. So what I will do, I will bring low to mid plus 1. I will bring low to mid plus 1, right? The moment I do this, low points here. Now this is our search space. This is our new search space from start of the search space, end of the search space. Now we are going to repeat the process. That's the thing that I said, right? Discard one half, keep one half, and repeat the process. Again, we will calculate mid. 16 plus 9 by 2. 16 plus 10 is 26. Minus 1 is 25. So 16 plus 9 is 25. 25 by 2 is approximately 12.5. So we can keep 12 as the mid. We can keep 12 as the mid. Now again a very interesting situation will come up. We can say that initially we had 17 elements. Now we are just left with 1, 2, 3, 4, 5, 6, 7, 8. We are left with 8 elements. So from 17 we reduce to 8. Half of the elements are gone. Now the moment on this search space you repeat the process, you got 41 as mid. Now this time, can we divide the search space into two halves such that both of the halves are different than each other based on some property? Let's see. This time the property that we are going to define is this. That is, the element pointed by mid is greater than the target. If this element is greater than the target, and this is a sorted arrangement of elements, all of these elements are greater than the target. Can I say that? If 41 is greater than 37, then all of these elements are greater than 41 also, right? So can I say this right half is of no use to us? This is of no use to us. Why? Because we are never going to find 37 here, because all of these elements are definitely greater than 37. Whereas in the left half, some elements are less than 37, some are equal to 37. And maybe if let's say there was 38, then some might have been greater than 37 also. So we cannot say for sure about anything on the left half, but we can with very surety say about the right half that Right half has all the elements greater than 37, discard it. And how do you discard right half? Your previously your end of the search space was 59. Now the end of the search space should come to 37. That is, high should come here. So what you can do? Discard right half. You do high is equals to mid minus 1. So whatever was the mid index, you just go just left to it. And you can see now from 8 elements, we are barely left with what? 3 elements. See, in just 2 iterations, how much elements we have reduced? Let's repeat. 11 plus 9, 20. 20 by 2 is 10. This is your mid. Okay. Now, mid is 31. Mid is, ARR at mid is 31. 31 is less than 37. So what I can say is, if 31 is less than 37, then everything to the left of 31 is also less than 37. I can never find my elements here. So what will I do? I will do low is equals to mid plus 1. So this left region is of no use to us because all of these elements are less than 37. I will do low is equals to mid plus 1. So mid was pointing to index 10. You go to 10 plus 1, 11. And now your search space left is of size 1. Now this time, if you calculate mid is going to be at the same index 11. This element is neither less than the target. This is nor greater than the target. This is actually equal to the target. This element is equal to the target. That means we have found our element. So we can have a separate check that if ARR of mid equals to target, we return mid because now you have your element which you wanted to find. That's it. That's it. This is how binary search will work here. And see, technically in just first iteration you do computation, second, third, fourth, in 4 iteration approx, you have resolved all of this array. And let's say if now in this case 37 is found. Let's say it was 38. Now you again calculate mid. Mid is 38. 38 is greater than 37. 38 is greater than 37. You do high is equals to mid minus 1. High comes here. Now you can see low and high have surpassed. The moment low and high surpasses, then there is no point of having start as low and end as high, right? Because now the whole search space converged. The moment you reach a situation like this, you can return minus 1. Because now the search space has been exhausted. You don't have any element left. That brings us to the point that you cannot find that element, and hence the answer is going to be minus 1. This is the whole algorithm of binary search that we can apply to this problem. In similar ways, there will be different problems in which we try to divide the search space into 2 halves, discard 1 half, accept 1 half, based on the fact what property differs both the halves, right? Now you might be thinking, okay, like seems like a dreamy solution to us, but what is the time complexity, right? So can I say that if I see with respect to this problem or any search space, if initially the size of the search space is n, then you reduce the search space size to n by 2, you discard half of the elements, keep half of the elements. Then you reduce your search space size to n by 4. You again discard half. So half of n by 2 is n by 4. You discard n by 4 and you keep n by 4. Then again you discard half, n by 8, and so on. At last, you will be left with 1 element before you actually stop the algorithm, right? Right? Cool. So we can say that in the zeroth iteration, the size of the search space was n by 2 raised to the power 0. In the first iteration, the size of the search space is n by 2 raised to the power 1. Can I say that? In the second iteration, size of the search space is n by 2 raised to the power 2. In the third iteration, size of the search space is n by 2 raised to the power 3 and so on. Let's say total number of iterations that we did was k minus 1, or let's say k, let's round off the figure, okay, that approx k iterations happened. Okay, so if total k iterations happened, so from 0 to k minus 1 there will be k iterations, right? So in the k minus 1th iteration, the search space size was 1, that you can write as n by 2 raised to the power k minus 1, right? If you have total k iterations, then it will be 0 to k minus 1, which is k, right? For example, here total 5 iterations happened because it is from 0 to 4, right? So in the k minus 1th iteration, you have size of the search space as 1, which we can write as n by 2 raised to the power k minus 1, because this is coming as a factor of 1 by 2. Okay. So how many total iterations we do? Total iterations is k, right? What is the value of k? Can I say I can calculate the value of k by comparing these two? I know that n by 2 raised to the power k minus 1 is equals to 1, right? Total number of iterations are k. I need to first of all get the value of k. Let's simplify. This becomes n is equals to 2 raised to the power k minus 1 taking log both sides. This will become log of n base 2 is equals to log of 2 raised to the power k minus 1 base 2, which implies log of n base 2 equals to k minus 1 log 2 base 2. What is log 2 base 2? Log 2 base 2 is 1. This implies log n base 2 is equals to k minus 1. K is equals to 1 plus log n base 2. Right. So the total number of iterations are log n plus 1, which is technically approximately log n. Right. So total number of iterations are approximately log n. And in every iteration, let's see what we are doing. We are calculating mid, low plus high by 2. Constant operation. Calculation of mid is a constant operation, right? Then we are checking if check, constant operation, constant operation, constant operation, constant operation, constant operation. So in every iteration, we are just doing constant operations. So total instructions we gave was k into c, because in every iteration you are giving some constant operations. This is 1 plus log n base 2 into c. And if you write it in terms of big O notation, time complexity will become order of log n. Why? C will be avoided as it's a constant multiplication. 1 is a lower degree term. Bases we never write. Time complexity of the solution becomes order of log n. So this solution worked in order of log n. Right? This solution worked in order of log n. And you can see a huge optimization we did. Why a huge optimization? Because let's say the size of the search space is, let's say 10 raised to the power 3. Then linear search approximately, in the worst case, will take 10 raised to the power 3 instructions. Whereas binary search approximately will take 10 instructions, because 2 raised to the power 10 is 1024. That's approximately 10 raised to the power 3 only. So you can see how huge of a difference it is. And the moment you increase the value of the size of the search space, if the size of the search space is 10 raised to the power 6, linear search will perform approximately 10 raised to the power 6 operations, whereas binary search will perform 20, because 2 raised to the power 20 is approximately 10 raised to the power 6. So if you do log of 10 raised to the power 6, it comes as approx 20. If you increase it to 10 raised to the power 9, then this is going to take 10 raised to the power 9, whereas this will become 30, and so on. You can see how much of a huge reduction we have done because this is working in order of n and this is working in order of log n. This is the power of binary search. This is the power of binary search, right? That you keep on dividing your search space into equal halves, discard one half, accept one half, and you are good to go, right? So if I want to write a complete algorithm of binary search, this is how it will look like. At least in this particular problem of lead code, I can say low is equals to 0 because start of the search space is our array, right? High is equals to arr dot size or length, whatever function you want to use. Let's say length -1. We say while low is less than or equal to high, we calculate mid. Mid is equals to low plus high by 2. And then we check if ARR of mid is equal to the target, we return mid because we found the element, right? Let's say the element to be found was 23 only. Target was 23. Then in the first iteration only, this will be the middle element, right? So let's just check that whether middle element is equal to the target or not. Otherwise, else if ARR of mid is less than the target, then what do we have to do? We have to discard left half. How do you discard left half? You do low is equals to mid plus 1, else. Now ARR at mid is not equal, not less than, so of course this is greater than. So in greater than, we discard the right half, right? And that's it. At last you return -1. Why you return -1? If you never returned from this while loop, this mid, if we never returned mid, that means this while loop ended. When will this while loop end? This while loop ends when search space is exhausted, right? If the search space has been exhausted and you never found the element, we are going to return a -1. That's it. You can bind this inside a function named as binary search. You'll pass your array, you'll pass a target, and that's it. This will be your clean and simple iterative implementation of binary search. Time complexity we have already discussed. If you talk about time, we have already discussed it is order of log n. If you talk about space complexity, then you can see we are not taking any extra data structure. We have not created anything which is going to be similar with the rate of growth of our given input size. So the space complexity is O of 1. That's it. That's binary search for you. This simple implementation can help you to understand and implement binary search. So we'll say, if you want to solve the same binary search problem from lead code, this one, we'll say let low is equals to 0, let high is equals to nums dot size, nums dot length -1. We'll say while low is less than or equal to high, we'll calculate mid, low plus high by 2. We'll check if nums of mid is equal to the target. We are going to return the mid. Can I say that? Else if nums of mid is less than the target, then we are going to reduce or remove left half. Low is equals to mid plus 1, else remove right half, high is equals to mid -1, right? If we never returned within the while loop, we are going to return -1 because we never found the element. That's it. This looks good. If you run the code, let's see what is the problem. So we have -1, 0, 3, 5, 9, 12. Index was 9. Okay. And while low is less than or equal to high, if nums of mid, we calculated mid here, is equals to the target, this should be it. So let's see, 0, 1, 2, 3, 4, 5. 5 plus 0 by 2 is 2. We got 3. 3 is less than the target. We do low is equals to mid plus 1. We go here, right? And low is equals to 5, high is equals to 12, and we divide. Okay, got it. So in JavaScript, we have to do math.floor, otherwise it is going to give us a decimal value. Cool. Let's run code. Let's submit. And in one shot, we have submitted the solution. This was binary search algorithm for this particular problem, which is technically the most trivial problem which a lot of people take as a reference-based problem to explain binary search. So if you want to understand linear search and binary search better, then this is a very, I would say, cool animation that you can look for. You can see, let's restart this. You can see both of the algorithms started together. It just discarded one element, whereas it has discarded half of the elements. Now only 3 elements have been discarded, and it is actually at its answer. But the sequential search, or you can say the linear search, will go on one by one, one by one. So you can see the step counter. This will technically will be done on the fourth step approx, third step approx, you can see, whereas this is going to take a lot of time. So this is the power of binary search. This is like, technically you can see how fast binary search is with respect to your sequential search or linear search. So this is a new problem coming in front of you, right? Let's start reading the problem and try to understand what the problem has to offer. The problem says that given a sorted array of non-negative distinct integers. So few important pointers here. Non-negative, that is everything is going to be greater than or equal to 0. Okay, because no negative number is there. Distinct, so all of the numbers are going to be different. So given a sorted array, so you have been given a sorted array, right? So we will here consider that this is sorted in ascending order. Okay, you have to find the smallest missing non-negative element in it. So there are a lot of elements inside the array. All of the elements are greater than or equal to 0. Every element is distinct. You need to find the first element which is non-negative and missing. And that is kind of like the smallest also. You can say first or smallest element that is non-negative and missing. Let's take an example. This will help you to get a better clarity. So you can see this is the given array. 0, 1, 2, 6, 9, 11, 15. All of the elements are non-negative. All of the elements are distinct. But the first non-negative element which is missing is 3, because 0 is present, 1 is present, 2 is present, but 3 is not present. So 3 is the answer. If you see this array, then inside this array, 0 is not even present. So 0 is the answer. We don't care about anything else. 0 should be the first element, right? It's not even present. Here 0, 1, 2, 3, 4, 5, 6, everything is present. So the first missing element is 7, right? So this is the situation in front of us. This is the situation in front of us. And we have to somehow figure out what is the first missing non-negative element, right? We need to try to solve the problem in as efficient manner as possible. So to start the discussion, what will be the brute force? What will be the brute force? You can say that we are damn sure that the elements will lie in the range 0 to some element m, right? 0 to m elements will be there. M will be some positive number. So what I can say is that, how about I loop over the array, right? And we check whether the first element is, or the 0th element is 0 or not. First element is 1 or not. Second element is 2 or not. Next element is 3 or not, and so on, right? We can say for I is equals to 0, I less than n, I plus plus, right? And let's say we say expected element is equals to 0. Initially the expected element will be 0, right? We will check if a of I is not equal to the expected element, right? That is, the current element is not equal to the expected element, then we are going to return expected element, right? Otherwise, if it matches, that is the current element is the expected element, for the next iteration I will increment my expected element plus equals to 1. That's it. This is a simple implementation without any brain we can put, right? Because we know that this is an ascending order sorted array. Everything is distinct. So even no repetition is altogether there, right? So every element is distinct also. That means all of these elements are going to follow a set pattern, that you wanted to have 0, then you wanted to have 1, then you wanted to have 2, and so on. So this set pattern is there. If this set pattern is there, let's follow the pattern. We say that we are expecting 0, then we are expecting 1, we will increment, then we'll expect 2, then we expected 3, but we were not able to find 3, so we'll say return the expected element. That's it. Time complexity order of n, right? Simple, basic, kind of like a linear search based approach. We were trying to search for an element, we went to every element one by one. If the current element is not the expected element, we just say that this is the missing element. But can we optimize? Can we somehow optimize? Let's try to figure that out. So if I take, let's say, this test case, this is going to be the test case that we need. 0, 1, 2, 6, 9, 11, 15. Right? This is the given array. Now just tell me, if everything is going to be sequential, what would have been the correct sequence? What would have been the correct sequence of elements where nothing is missing? The correct sequence of element would have been 0, 1, 2, 3, 4, 5, 6, and so on. This would have been the correct sequence of elements. And can you see that this correct sequence of elements is actually the indexes of the given array? So we can say that if every element is present, then element with value I must be present on the ith index. Can I say that? Element must be present on the ith index, which should be I. So if 0 is present on the 0th index, we are good to go. If 1 is present on the first index, we are good to go. If second is present on the second index, we are good to go. Is third, or I would say 3, present on the third index? No. So this is the problem, and we are going to return 3. Right. So based on this observation, we can somehow improve our solution. Let's see. Let's try to apply binary search here. What was the condition of binary search? The condition of binary search is, can we divide the search space into 2 halves such that one half is different from the other? Okay. Let's consider a case like this. Okay. For this test case, the answer should be 6, right? Okay. What is a search space? Search space is going to be the given array only, right? This is something that we can define, that our search space will be given array. Within the given array only, we are going to find the missing element, right? Missing element is going to be found within the given array only. Okay. Now, if we divide them into 2 halves, if we divide the array into 2 halves, this is 5, 6, 7, 8. This is going to be the middle element. Okay. Now just tell me, can we divide the search space into 2 halves such that both of the halves are somehow different? Let's see. Can I say that if ARR of mid is equals to mid, if this is the condition, that is at the fourth index we have a value 4. See, this is index 0, 1, 2, 3, 4. So at the fourth index we have a value 4. If this is the case, then we can say that everything less than mid is also present. Can I say that? Why everything less than mid is also present? Because if there was any element missing, then the order would have shuffled by the time you reach the element mid, right? For example, if 2 is not present here, we have 3 here, we have a 4 here, we have a 5 here, then on the fourth index we have a 5, right? In this case we can say there was some missing element. But if the current element is equal to mid, like the element at the mid index is equal to mid, that means we can say that everything from 0 to mid is present. Everything from 0 to mid is present, right? And this is the left half. So left half is absolutely correct. We don't want to hamper the left half. Left half has everything present inside it. But can we say the same about the right half? Maybe not. In the right half, on the fifth index you have 5, but the remaining elements doesn't comply. So for the left half you have this property assured, but the right half doesn't follow this property. So based on this property, we can definitely divide our search space into two halves. We don't need the left half because left half is all okay. We can say discard left half and move to the right half. How do we move to the right half? Low is equals to mid plus 1. So we are going to say low is going to be moved here. And now my search space reduces to this. My search space reduces to this. Okay. Now let's calculate mid again. So 5, 6, 7, 8. 8 plus 5 is 13. 13 by 2 is this, mid. Now in this case, here you can see that we come to the else part. That is, ARR of mid is not equal to mid. ARR of mid is not equal to mid. This is the condition here, right? Now, if ARR of mid is not equal to mid, can we divide the search space into two halves somehow? We can say that this index is an index where you are not following the property. This is an index where you are technically not following a property, right? Why? Because this index mid is what? 6. If everything was correct, then technically 6 would have been present here. But 6 is not present here, right? 6 is not present here. We have 16, which is not equal to 6. So I can say that this is an index where we have a missing element, right? This is an index where we have a missing element. But the story doesn't stop here. Why? Because we have to find the smallest missing, right? We don't have to find any missing. We have to find the smallest missing. Now, how do we know whether this is the smallest missing or not? Because maybe this was 15, right? So the smallest missing element now is 5. It's not 6, it's 5. So this 16, the moment you find something where the index is not equal to its value, we can say that this can be a potential answer. For a case like this, 16 is a potential answer. But maybe we can find something better than 16, right? In case of 15, we will be able to find something better than 16, right? So what will we do? We can say that if 16 is at index 6, then we can say that 6 is one of the best answers. If not the best, then definitely it's one of the best candidates to become the answer. I will keep an answer variable and I will say that answer is equals to I, because now we know that either something at index I will be my answer or less than I will be my answer. Why? Because I don't need to consider anything greater than I. So if I divide my search space into two halves, then I can say that in this kind of a case, we know the second half everywhere element doesn't match the index. So all of these elements are missing, but this mid is the best possible candidate among these elements, right? So in the right half, we don't want to go. Why? Because the middle element or the mid element is the best candidate. I have stored it here. This should not be I, this should be mid. This should be mid. And I will say that maybe something better is found on the left half. So I will discard my right half. The whole right half will be discarded. Discard right half. And how do you discard right half? You can just say high is equals to mid minus 1. So high comes at the same place where low is. Okay. And again we will calculate mid. So mid is going to point at the same index. Okay. Now, is ARR at mid equals to mid? Is ARR of 5 equals to 5? No, it is 15. So we come here. And now we update our answer. We found 6 as a good answer, but now we have found an even better answer. So now answer will become mid. Mid is what? 5. And we do high is equals to mid minus 1. High goes here. And that's it. Now you have reduced your search space to 0. There is no element left in the search space. And your final answer is going to be present inside answer, which is technically 5. Right? This is the essence of binary search in this problem. Let's take one more example. Let's take, let's say this 0, 1, 2, 3, 4, 5, 6. Okay. Cool. Let's calculate low, high, and let's calculate mid now. So this is going to be mid, 6 plus 0 by 2. Is ARR at mid equals to mid? Let's bring this conditions directly here. Copy. Paste. Okay. So is ARR of mid? Let me write the indexes also. These are the indexes. Is ARR of 3 equals to 3? Yes. So we know that everything less than 3 is also correct. We will discard this half. And I will do low is equals to mid plus 1. Okay. Cool. Now, again we will calculate mid. This is mid. Is ARR at mid is equals to mid? Yes. ARR at 5 is equals to 5. We'll again discard the left half. So this is the left half. We'll discard. Low also comes here. High also comes here. Okay. Low also comes here. High also comes here. Now, again mid you will calculate. Again you will calculate mid. And you can say, is ARR of 6 equals to 6? Yes. So you'll again do low is equals to mid plus 1. And now low and high are exhausted. Can I say that? Low and high are exhausted. In this case, now you can see this answer was never even encountered, right? So what I can say is let's keep the default value of answer as ARR.length. What was ARR.length? ARR.length was 7, right? So I can say that initially I'll keep answer as 7. We iterated over the loop. We never got into else. My final answer is 7. Can I say that? Can I say that? Right. So this test case can be handled by just initializing your answer with ARR.length. And how 7? Because 7 is the first non-negative number which is missing. So what are the non-negative numbers? 0. Is 0 present? Yes. 1. Is 1 present? Yes. 2 is present. 3 is present. 4 is present. 5 is present. 6 is present. Is 7 present in the array? No. Because you have exhausted the array. So answer is going to be 7. And you can see that is the expectation here also. You have 7. For the middle test case, you can just keep a corner check. Before even starting the algorithm, you can just check if ARR of 0 is not equal to 0, return 0. This can be a corner check that you can keep. Right? You can just handle it as a corner case. Okay. Let's take one more general case as the example. Okay. So this is a 10 length array. We keep low here, we keep high here, and let's cut out this. Copy, paste. Okay. This time answer is going to be initialized by ARR.length. What is ARR.length? 10. So we'll assume that maybe 10 is our answer, but we will try to improve. We'll calculate mid. 9 plus 0 by 2 is 4. So we got mid here. Okay. Is ARR of 4 equals to 4? Is ARR of 4 equals to 4? No. So we say that maybe this is the index where we will find our answer, because maybe 4 is the element which is the first smallest missing element. So we'll say answer is equals to mid. So answer becomes 4. And you say that maybe this is our index where the first smallest element, missing element should have been there, or something better than this on the left side. Why? Because on the right side everything is, I would say, missing. So if everything is missing, then 4 is definitely the best answer among 4, 5, 6, 7, 8, 9, right? Because 4 is the smallest, at least in this region. So maybe we can find even smaller than 4, which is better. So I'll discard my right half and I'll do high is equals to mid minus 1. Okay. Let's calculate mid again. 3 plus 0 by 2 is mid, is 1. Okay. Cool. Now, we can say, is ARR of 1 equals to 1? Yes, ARR of 1 is equals to 1. So we can say that everything to the left of 1 is all correct. We will never be able to find anything. We won't be able to find any answer altogether. We'll do low is equals to mid plus 1. 3 plus 2 by 2. 3 plus 2 by 2 is what? 2. 5 by 2 is 2. So our mid comes here only. This is mid. Okay. Is ARR of 2 equals to 2? Is ARR of 2 equals to 2? Yes. So I can say that everything to the left of 2, this is the only left region, is all good. I'll do low is equals to mid plus 1. So low and high comes at the same position. Now let's calculate mid. This is mid because 3 plus 3 by 2 is 3. Is ARR of 3 equals to 3? No. ARR of 3 is equals to 13. That means we have found a better answer. I'll update answer to be mid. Answer becomes 3. And high is equals to mid minus 1. High comes here. And that's it. You have converged your algorithm, right? So your final answer should be 3, right? Because 3 is the first missing element. So I can just use this algorithm. Copy. Paste. I can say that answer is going to be initialized with ARR.length, while low is less than or equal to high. Mid is equals to low plus high by 2. Right? And before this, you can say low is equals to 0, high is equals to ARR dot length minus 1, right? And this answer initialization you should do outside. That would be better. Okay. And just our corner case check we will add. We will say if ARR of 0 is not equal to 0, we return 0. That's it. This is our function. This is going to be the simple implementation that you have to do. Just keep the corner check for this. Initialize answer to be ARR.length. Set your search space. Reduce your search space every time. Finally, return answer. Finally, return answer. That's it. That's it. And if you see the time complexity, you can see it's a simple binary search only, right? Every time from n, you are going to n by 2, then you are going to n by 4 and so on. So the time complexity is going to be order of log n. And the space complexity is going to be order of 1 because we have not taken any other data structure in order to implement this algorithm. So this is going to be the simple implementation that you can do for actually calculating the first missing, I would say, non-negative number in a sorted array of distinct elements. So till now, whenever we have to calculate a mid, what algorithm we use? We say mid is equals to low plus high by 2, right? Somehow this. Even in merge sort or like any sorting algorithm which somehow divides the array into 2 parts or something, there also you do something like this, low plus high by 2. Now the question is this always correct? No. This, I would say, formula is not always correct. In a lot of languages, inclusive of JavaScript, whenever you have a number, like in a lot of languages like C++, JavaScript, Ruby, whatever languages you consider, and you are having a number, even in Java, this number has generally a upper limit, like the biggest number that you can store. Generally, this number is having a upper limit, that what is the biggest number that you can store, right? Okay. Having said that, if you will add two very big numbers, which is technically very close to the upper limit of your number storage, like your variable which is storing a number cannot store a number beyond a certain limit. Okay. So if you are going to add two values, which are of very big range, then technically this sum can go beyond, or it can overflow. This sum can overflow the max number range. This sum can overflow the maximum number range. When this overflows, then it will create issues, right? In some languages, this will, if you try to overflow, for example, let's say if your maximum number range is 32, and if your sum becomes greater than 32, then low plus high will go in the negative direction, right? And even if you are dividing, before the division, plus addition will happen, right? This addition will cause this overflow, which can create issues. That is why we have to modify the formula. We say mid is equals to low plus high by 2. Inside this formula, in the numerator, I will add low and subtract low. If I add low and subtract low, everything remains as it is, right? Low plus high plus low minus low. This is the original formula only. Let's refactor. Low plus low by 2 plus high minus low by 2. This becomes 2 low by 2 plus high minus low by 2. This becomes low plus high minus low by 2. So this is going to be our new modified midpoint formula that we can use in order to calculate mid of a range, or kind of like the two values. And why this is better? Because this time you are subtracting two very big values. If you add two very big values, they become an even bigger value. But if you subtract two very big values, they become an extremely small value, right? So you take a very extremely small value and even divide it, so it becomes even smaller, and then add to low. Whereas previously you are just directly adding high to low. So there is a very less chance that this time you will overflow. And you can even see this formula with respect to this. If let's say this is your search space, low, high, and this is mid. You want to calculate mid, right? Now mid is at some distance x from L or low. I can say low plus x becomes equals to mid. This midpoint is at a distance x from low. What is this distance x? This distance x is your total range. What is the total range? High minus low by 2. So this x value is what? High minus low by 2. So if you add high minus low by 2 inside low, high minus low by 2 inside low, you will get the midpoint. So you can even visualize it like this, or you can manually derive mathematically. In both of the cases, whenever you are going to use midpoint, try to use this formula instead of low plus high by 2. This will help you to avoid overflow in any language that you are using. I hope this basic concept is clear to everyone. So this is a new problem in front of us, right? Name of this problem is sometimes also called as lower bound. Okay. So what the problem says is that given an array of integers arranged in ascending order and a value x. Okay. So you'll be given an array where elements are arranged in ascending order, and you will be given a value x. You need to find the index of the first element which is greater than or equal to x. So you need to find the first element, or the index of the first element, which is greater than or equal to x.
So for example, x is 3. So the first element greater than or equal to 3 is 3 itself. So the first index at which 3 is present is 3. This is the index 3. If you say x is equals to 4, now 4 is not even present. So the first element greater than or equal to 4 is this element 5, and the index of 5 is 6. If you say x is equals to 5, then the first element greater than or equal to 5 is this 5 only, and the index of this 5 is 6. Right? So this is the problem statement in your hand, and sometimes this problem is also referred as founding the lower bound for x. That given a sorted array, find the lower bound for an element x. Okay, so the lower bound for element x is equals to 3 is 3, for 4 it is 6, for 5 it is 6, right, and so on and so on. This is the problem in hand, and we need to figure out the solution to this problem, right? We will try to solve this problem in order of log n, right? This is the expected time complexity for the problem. Why? Because if you just directly see the brute force, then at any point of time, if you have an element, like in the brute force, you can go to every index. If the current element is less than x, avoid, less than x, avoid, less than x, avoid. If the current element is greater than or equal to x, so the first element that you encounter which is greater than or equal to x, that particular index is your answer. Right? This is kind of like a linear search based approach, right? Which will be order of n. We don't want this basic brute force, but we want to somehow optimize. So we're going to see an optimized solution. Copy, paste. Okay. So this is the array in front of us. Let's say x is equals to 4. Okay. Let's consider x is equals to 4. Now, how can we solve this question? Now, whenever you have a logarithmic complexity, you want to find something, and you are able to see that, okay, there is kind of like a search space that is getting formed. You should try to apply binary search. And how do you apply binary search? Check that if the search space is getting formed, you can divide the search space into two halves, where you discard one half and accept one half based on the fact that both of the halves are different based on some property. Okay. So what will be the property? So let's say this is the search space, because now inside this array only our lower bound is going to be present. So of course the array is going to be the search space. Let's put the indexes 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now, how can we solve this question? Generally, I ask students to visualize it in the form of true and false. What is true and false? So if this is the array, I write it in the form of true and false like this. For x is equals to 4, true, 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 or better would be this. False, 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 true, true. For x is equals to 3, false, 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 true, 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 true. Okay. For x is equals to 5, false, 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 true, true. Now you might be thinking, sir, what are you doing? Why are you writing so many falses and trues? What is actually going on? So technically, for any test case, if you visualize this array in the form of trues and false, then technically your problem reduces to finding the first occurrence of true. Finding the first occurrence of true. So here you can see the first occurrence is true here. First occurrence of true is here. First occurrence of true is here. Now you're thinking why I'm saying it like this. Let's see. So here in this given array for x is equals to 4, if you divide your search space into two halves, you get mid here. Okay. Now just think about it. If the value at mid is less than 4, if this value is less than x or 4, then I can say that everything to the left of it is going to be less than x. Can I say that? You can say that in this case I encountered mid here. So if I encountered a false, everything to the left of it is also going to be false. Everything to the left of it is also going to be less than x. And I know I want the first element greater or equal to x. I don't want less than x. If I don't want less than x, I can discard my whole left half. This whole left half will be discarded. And how do you discard the left half? You move low to mid plus 1. Okay. Now again, let's try to calculate the mid. So 7 plus 4, 11 by 2, 5, mid. Now again, you can see you got in this region mid here. The moment you got a false, that is ARR of mid, this is 3 is less than 4. So everything to the left of 3, that is this whole left area of the search space, is less than x. We can never find our answer here. I'll again do low is equals to mid plus 1. I'll do low is equals to mid plus 1. Now 7 plus 6, 13 by 2 is this mid. Mid will be pointing here only. Now, is this element less than x? No. 5 is greater than or equal to x. You can see this is true. The moment you find an element which is greater than or equal to x, that element might be our answer. See, technically this 5 is only our answer. So that element might be our answer or not. So first of all, let's just consider this might be our answer. If this might be our answer, then we will maintain an answer variable. And we say else answer is equals to mid. Right. Now you might be thinking in which case this might not be our answer. Okay. You might be thinking about that. So let me do one thing. In which case this won't be your answer. Let's see. So let's modify your array, or let's say modify your input. Now let's say let's consider 3. Okay. And let's add one more element, 8. Okay, cool. Now let's see. This is low, this is high. Okay, this is low, this is high. If you try to divide your search space into two halves, this is going to be the mid. Is 3 less than 3? No. That means this 3 is greater than or equal to 3. So this might be your possible answer, right? This index might be your possible answer, because if this was a 2, then this was our final answer. But this is not a 2, this is a 3. So now we can say that if you see the search space, now you have two regions. In one region, everything is greater than or equal to x. We are damn sure this right half, everything is greater than or equal to x. And in this whole right half, the best possible answer is going to be mid. If you just consider this right half, the best possible answer is going to be mid. So I'll store that answer and I can say that I will never find anything better than mid on the right half. Let's write it. We won't find anything better than mid on right half. So what we will do, we will converge to the left half. How do you converge to the left half? You put high here. High is equals to mid minus 1. Okay, let's calculate mid again. Now 3 plus 0 by 2 is 1. We calculate mid again. 2. Is 2 less than 3? Yes. If 2 is less than 3, then this whole region is never going to be your answer. So the two parts of the search space are dependent on the fact that this whole region is less than the answer. The right region may be less than the answer or maybe more than the answer. We are not sure. So if we take a decision, we say that this region can never give you anything. So let's move low is equals to mid plus 1. Now 3 plus 2 by 2, mid comes here. This 2 is again less than 3. What will you do? Low is equals to mid plus 1. Now both low and high are pointing to 3. Now mid also comes as 3. Okay. Is 3 less than 3? No. So we'll say that we found something better, because the previous answer was 4, right? Now we will be able to find 3, which was something better, and that's why we reduced previously to the left side, right? Because We already found that this is the best answer in the right half, but maybe something better than this exists on the left half, which was this. And technically we arrived here. So we check, is 3 less than 3? No. So answer is equals to mid. Mid is index 3. And we do high is equals to mid minus 1. High comes here. And low and high have passed. And that's it. That's it. So technically, if you see this here, in this case of x is equals to 3, you wanted to find the first true. When you got this true, you know that everything to the right of true is always a true. So this might be your answer, but maybe you can find another true to the left of it. So we reduced on the left side and avoided the right side, and so on. The moment you encounter a false, you know that everything to the left of false is always a false. You can never find anything, so you reduce yourself to the right side, and so on. That's it. That's it, right? So if I want to write the algorithm, I can say lower bound. You will be given an array. You'll be given x. You say low is equals to 0. High is equals to arr dot length minus 1. While low is less than or equal to high. Mid is equals to low plus high minus low by 2. And we check if arr of mid is less than x. We do low is equals to mid plus 1. Else we do answer is equals to mid, high is equals to mid minus 1. At last we return answer. That's it. That's it. This is going to be the simple implementation. This is going to be the simple implementation for the lower bound function. Can I say that? Right. And the whole implementation we have done is using binary search. You can see this is the search space. Every time you reduce your search space by 2, you reduce your search space by 2 again and again. Can I say that? Right. And now you might be thinking, what will be the case for something like x is equals to 9, which is not even present in the array? If something is not even present in the array, right, then I can say that you can initialize your answer from arr dot length. Okay, you can initialize your answer with arr dot length. Let's see this case. So 1, 2, 3, 3, 4. And x was equals to, let's say 6. So this is low, this is high, and answer is equals to arr dot length. Arr dot length is 5. We check the mid. Is the mid less than 6? Is the mid less than 6? Yes, mid is less than 6. So everything to the left of mid is never going to be the part of your answer. Low is equals to mid plus 1. Again you calculate mid, it will be less than 6. Again you calculate mid, it will be less than 6. So never you will update your answer, right? So finally your answer is going to be arr dot length. Can I say that? Right. And corner case. If let's say x is equals to minus 1, then you can just manually check that if arr of 0 is greater than or equal to x, then you have to return 0. Can I say that? You can manually keep this as a corner case, right? Or if you don't even keep this as a corner case, let's see what will happen in our normal algorithm. Low, high, mid. Is 3 greater than or equal to x? Yes. So definitely 3 is our 0, 1, 2, 3, 4. Index 2 is our better choice. And we do high is equals to mid minus 1. Now 0 plus 1 by 2 is 0. Mid comes here. Is 1 greater than or equal to minus 1? Yes. So index 0 is going to be a better answer, and you do high is equals to mid minus 1. This time low and high passed each other and your algorithm ends. So you can see still you are able to get the answer 0, right? So either you can keep a separate if check, or our loop is going to definitely handle it. The time complexity is going to be order of log n, and the space complexity is going to be order of 1. As simple as that. This is going to be a core, simple, crisp implementation of lower bound using binary search. So let's try to implement the lower bound function. So function lower bound, you will be given an array and you will be given a value x. You set your search space. You initialize your answer to be equal to arr.length. And you say while low is less than or equal to high, you calculate mid to be low plus math.floor of high minus low by 2. And you check if ARR of mid is less than x, you're going to go low is equals to mid plus 1. If it is greater than or equal to x, then maybe we found a better answer. And we can find even better answer on the left side. So you reduce your right half by doing high is equals to mid minus 1. At last, you are going to return answer. That's it. So if let's say we take a basic example, 1, 2, 2, 3, 3, 3, 5, 5, 8. And let's say if I pass x as 3, you can see we got the index 3, that is the correct answer. If I pass it as 4, we got 6. For 5 also it should give us 6. Okay, for let's say 10, it is giving us 9. So if you see 4 and 5, so that's the array.length, that's correct. If you go for minus 2, it is giving us 0. So all of the test cases are passing. And if I write the time and space complexity, the time complexity here is order of log n and the space complexity is order of 1. As simple as that. So this is going to be the crisp, simple implementation of lower bound using binary search. Now we know about lower bound, right? We know about lower bound. Just like lower bound, we have upper bound. What is upper bound? Given an array of integers arranged in ascending order and a value x, find the index of the first element which is greater than x. Now this time you just want to find greater than x. You don't want to find greater than or equal to x. Okay. So if I bring the same test case here, copy, paste. Now this time the answer is going to change. Now the first element greater than 3 is 5. This is at index 0, 1, 2, 3, 4, 5, 6. This is at index 6. So answer is going to be 6 here. First element greater than 4. Again 5, which is at index 6. First element greater than 5 doesn't exist, so it will be array.length. So 4 elements here, 4 elements here, array.length is 8. Right. So this time you need to somehow try to figure out upper bound. Upper bound is considered as greater than x. Lower bound is greater than or equal to x. Upper bound is greater than x. Right. How can we solve this? If we have already solved the problem of lower bound. So in lower bound, what we used to do? If the value was less than x, we discarded the left half. Otherwise, it is greater than or equal to x, then we accepted the right half, right? So technically speaking, if you have this array in your hand, copy, paste, let's add a 8 here, 0, 1, 2, 3, 4, 5, 6, 7, 8. Now this is going to be the mid value. This is low, this is high. Now you can see, if the value of x is 3 only, if the current value, if a of mid is either less than x or equal to x, in both of the cases, this index is not acceptable. Can I say that? Because I just want greater than x. So if you are at an index which is less than x or equal to x, then everything to the left side will also be less than or equal to x. I don't need this. So you go to the right half. Otherwise, Otherwise, if you calculate mid, 8 plus 5, 13, by 2, 6. If you calculate mid. Now this element, is 5 less than or equal to 3? No. So 5 is an element greater than 3. Now maybe this 5 is answer because everything to the right of 5 will also be greater than 3. So in this whole right range, 5 is the best suitable answer that we have got. So I will say answer is equals to mid. And then maybe something better than this index, this element 5 at index 6 exists on the left side, because on the right side we can never find anything better than this element. I can never find anything better than this element on the whole right side. So I will go to the left side. How do you go to the left side? High is equals to mid minus 1. That's it. So if I just pick the same algorithm of lower bound that we wrote, same algorithm if I pick, let's just rename it to upper bound and just update this condition to be greater than or equal to x. In both of the cases, you discard your left half. That's it. This is upper bound for you. Time complexity remains same log n. Space complexity remains same, order of 1. So very simply, we have also implemented upper bound for us. It's new question, but same approach altogether. So now if you want to implement upper bound, let's paste the code of lower bound here. I'll just rename it to upper bound and then just make less than x2 less than equal to x. That's it. This is now going to become upper bound. Let's try. For minus 2, upper bound is still 0. Very good. For 3, upper bound is 6. For 4, upper bound is 6. For 5, upper bound is 8. As simple as that. And in logarithmic time, we have also calculated upper bound. Now this is a new problem coming to us from LeetCode, problem number 34. Find first and last position of element in sorted array. You can see more than 15,500 upvotes marked as medium. I will say it as easy medium. If you see the number of companies it has been asked in, you can see humongous number of times it has been asked. Facebook 5 times, Amazon, Intuit, Apple, Bloomberg, Google, Adobe, Samsung, Microsoft, Uber, LinkedIn, Yahoo, all the big tech giants, you can see it has been asked in. The problem says that given an array of integer nums sorted in non-decreasing order. Okay, so this array of integer nums has been sorted in non-decreasing order. Okay, what is non-decreasing order? Ascending order. So it is just to confuse the reader. This is ascending order only. Okay, so you have an array sorted in ascending order. Find the starting and ending position of a given target value. So you will be given a target value and you need to figure out what is the starting index and the ending index. If the target is not found, you need to return -1 and -1. Okay. So now this is going to be a very simple question. This is going to be a very simple question. Let me see. Let me show you. So if you have, let's say, 5, 7, 7, 8, 8, 10. And let's say the target is 8. Now you need to find the first occurrence of 8 and last occurrence of 8. So what is the first occurrence of 8? First occurrence of 8 I can just write as lower bound, because the first element greater than or equal to 8. If 8 is present, this is considering if target is present, then first occurrence will be lower bound. First occurrence will be lower bound. And the last occurrence is going to be what? If you calculate upper bound of 8, upper bound of 8 will be 10. So just before 10. So if target is present, then last occurrence will be upper bound -1. See, upper bound is going to be The first value greater than the target. So the last value equal to the target is going to be just to the left of it. As simple as that. And if let's say the target is not even present, how to check? If target is not present. If you want to check whether target is present or not, just calculate lower bound. Just calculate lower bound. If the element at lower bound is not target, then it's missing. Can I say that? We can just calculate lower bound. For example, 6. Now for 6, the lower bound will be, for 6, the lower bound is going to be 7. Now you check whether the index, or I would say the element pointed by the lower bound index, is this element equal to target? No. That means this target is missing, because if this target would have been present, then lower bound gives you greater than or equal to target, right? So if the target is present, you will go to the equal to target value. Hence we can say target is not present. So all you have to do is first calculate your lower bound, check if the element is present or not, then calculate your upper bound, and then finally you can return lower bound comma upper bound minus 1. This is going to be your answer. If the element is not present, you can return minus 1 and minus 1. So you will first calculate lower bound, that's log n. Then you will again calculate upper bound, that's log n. Log n plus log n is going to be order of log n. So this problem can be solved for an n length array in order of log n using binary search. So you can see the whole story connects, right? You calculate lower bound, you calculate upper bound, make a mix match here and there, and boom, the problem is solved for you. So in order to implement what we am going to do, I am going to first of all copy my lower bound function here. Then I will copy my upper bound function. Okay, both of the functions are copied, right? Now let's start the implementation. So I will first of all go and check, let lower bound is equals to lower bound nums comma target. Okay, if lower bound is greater than or equal to nums dot length, if the lower bound is greater than or equal to nums dot length, for example, if let's say the target was 11, then in that case lower bound will be what? ARR dot length, right? In this case, or if nums of lower bound is not equal to target. In both of these cases, I can say target is missing. If target is missing, I will return minus 1 comma minus 1. Otherwise, I'll calculate upper bound. I calculated upper bound. At last, I can return lower bound comma upper bound minus 1. Right. This looks good to me. If I run the code, let's try with a few cases. Okay, works for the first case. Let's make it 6. Okay, works here also. Inside an empty array, let's see what happens for an empty array. This is a corner case, I believe, but let's see. Okay, handles empty array also. Looks good. Let's try to submit. And boom, done. Very gracefully. If you have your lower bound and upper bound implemented, then the whole problem will be very easily solved. You can see it has been marked as medium, but that's why I was saying that I believe that it is easy medium.
So this is a new question coming from interview bit. Fairly simple, fairly straightforward. The question says that you have been given a sorted array of size n. Find the number of elements which are less than or equal to b. So if you want to find, if let's say b is 4 and this is the array, you want to find how many elements are there which is less than, so you can say you need to find the number of elements which are less than or equal to b. Okay, so what you can do is you can find the upper bound of b. Upper bound of b here is going to be 6. That is the first value greater than b. Once you find the first value greater than b, all the values to the left of it is going to be less than or equal to b. Can I say that? So that's why here we get an answer as 4. And what is the upper bound of 3 here? That is 5. So here we will get an answer as 2. So you can see Pretty straightforward. So you can just apply your upper bound function and get this problem straightforward submitted. So we have a new problem coming from LeetCode, problem number 33, one of the most famous questions called as search in rotated sorted array. It's marked as a medium problem and you can see a whooping 21,900 upvotes. If you can see previously, this has been asked in companies like Apple, Google, Uber, Yahoo. You can see Bloomberg, Microsoft, Adobe, all of these companies have previously asked this question, right? One of the most frequently asked question you can say, right? Apart from that, this same question was asked to me as well in one of my interviews at Interview Bit, right? In the first round, first face-to-face round of Interview Bit, this question was asked to me as well, right? So what the question says that is that there is an integer array num sorted in ascending order, right? So you have a numbers array. It is first of all sorted in ascending order, that is increasing order with all distinct values. So you have all different values altogether. Prior being passed to the function, nums is probably rotated at an unknown pivot index x. So there is some rotation that has happened, right? Such that the resulting array is num of k plus 1, so on and so forth, up till num of n minus 1, and then num of 0, 1, 2, and then k minus 1. For example, if this was the array 0, 1, 2, 4, 5, 6, 7, this was the initial array, which was initially ascending order sorted. You can see initially it was ascending order sorted. So if you assume that this is your given array, this might be rotated at a pivot index 3. You are not known that at what pivot it has been rotated, but some rotation is there. So post the rotation, it will become 4, 5, 6, 7, 0, 1, 2. You can see these elements are now at the start, right? Given the array nums, after some possible rotation and an integer target, you have to return the index of the target if it is in nums, or you have to return -1 if it is not present. Try to write an algorithm in log of n time complexity, right? So a very, very interesting question, and definitely I would like to give a thorough example for this, right? So let's say initially you were given an array like 2, 3, 6, 8, 9, 11, 13, 17, 19. Okay. Let's say these are the elements, and you can see currently this array is sorted in ascending order. All of the elements are arranged in ascending order. Now let's say some possible rotation happened. So how the rotation will happen? You will pick up one element from the start, move it to the back. Okay. This is one level of rotation. If one more rotation happens, then you are going to bring one more level at the end, one more element at the end, right? So however number of rotations happens, those many number of elements will move to the end. Now you can see this array has been now rotated. After rotation, post rotation, how the array will look like? The array will look something like this, right? And let me draw it properly. So the array will look something like this, right? And something like this. Okay, there will be a subtle gap between these, right? So this will be a approximate graph of your corresponding array, right? There will be a slight dip. You can see these elements are increasing, and then there is a slight dip, and then these elements are increasing as well. And then you will be given some target element, for example, in our case, let's say it is 6. You have to find that target element. Okay. Now it's a very, very interesting question, right? Why? Because the question asks us to solve this problem in log of n time complexity. If you go via brute force, that you have to search an element, and this doesn't look like a sorted array, right? If you go via brute force, then a basic linear search will help you. Why? Because you just go to every element. Is this value a 6? No. 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 Is it equal to the target? No. Is it equal to the target? No. Is it equal to the target? Yes. This value is 6. Hence, we found the value at this corresponding index. Fair enough? Linear search will give you the time complexity as order of n. That's the basic brute force that you can apply. Now, you might be thinking that how can we further solve the question? Now we have learned one more searching algorithm called as binary search. And one very interesting property about binary search is that it is not necessary that binary search will only be applied to a sorted array. A lot of time people think that binary search can only be applied to a sorted array. That's not actually true. Binary search
can be applied to even an unsorted array. You can see currently this is unsorted, right? It has some properties going on, but overall it is unsorted, right? Then you might be thinking, then how do we understand that where binary search can be applied and where it cannot be applied? So in order to identify whether you can apply binary search or not, you have to just see one simple thing. That is, if you have a search space, I believe everybody knows about search space. That is the entire set of data that like inside which you have to search for the element. If you can divide the search space into two parts such that one part is different than the other part. This is the left part. This is the right part. And one property that you can identify is that based on some property, left is different than right. Based on any property, any concrete property, if you can identify that the left half is going to be always different than the right half, and then you can either pick one half and reject one half, right? You can either pick the right half, reject the left one, or pick the left one or reject the right half. Then you can apply binary search there. Any search space which can be divided into two parts such that two parts are differing on some property, and you can then, based on that property, reject one part and select one part. In that case, you can apply binary search. Let me show you with an example here. Now let's say you want to find 6. Now just think about it. Let's say you want to apply binary search, okay? 0, 1, 2, 3, 4, 5, 6, 7, 8. What is the midpoint here? Midpoint is this 17. This is the midpoint, right? Now, what property we can devise such that the left part is different than the right part? Can we devise some property? Yes, we can technically devise some simple properties here. What we can say is that you can compare the midpoint with the target element, right? Generally in normal binary search, this is what you do. You compare the midpoint with the target element, move left or right. But here, there is one very special thing that is there. After rotation, you can see the graph is something like this. And I have drawn it very carefully. Why? Because post rotation, this is going to be the point where the left part is also sorted, right part is also sorted. But one thing to carefully note is that all the elements in the right part are definitely going to be lesser than all of the elements of the left part. That's why you can see all of the elements of the right part here I have drawn as lesser than all of the elements of the left part, right? That means this is one range, this is one range, right? So actually you can have two cases. You can have a case like this. You can have a case like this, right? Or you can have a case like this, right? What is different in these two cases? In these two cases, you can see the transition is happening at different point. For example, here you can see the right part is having more elements, left part is having less elements. Here left part is having more elements, right part is having less elements. For example, here you can see that you can say 9, 10, 11, 1, 2, 3, 4, 5, 6, 7. Here you can say 5, 6, 7, 9, 10, 11, 1, 2, 3, 4. Okay. So you can see here on the left side, there are less elements. On the right side, there are more elements. Here on the left side, there are less elements. Sorry, more elements here. And on the right side, there are less elements. Now, if you will calculate midpoint, then most probably your midpoint is going to lie somewhere here. In this case, your midpoint will lie somewhere here. In this case, your midpoint will lie somewhere here, right? Or maybe a bit close, right? Somewhere here. So in both of the cases, your midpoint is going to lie on one of the longer edges, right? That means, and you might be thinking, sir, okay, you are saying so. How can we identify? You can very easily identify that whether your elements are lying, the midpoint is lying on the upper curve or the lower curve, upper curve or the lower curve. Let's see. Here you can see the target was 6. You got the midpoint as 17, right? You got the midpoint as 17. First of all, you have to figure out where is this midpoint. If this midpoint is greater than the ending element, can you guys see that? Right? If this midpoint is greater than the end, right, and it is lesser than the left, so you can say this is the low, this is the high, right? That's what we actually need to check for, right? Now, if you carefully understand, in this case, 17 is bound to be less than 9, right? Let's see here. In this case, midpoint is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4. This is the midpoint, right? This is the midpoint, 2. And in this case, the midpoint is 0, 1, 2, 3, 4. 10 is going to be the midpoint, right? Okay. Now, in this case, you can see 2 is less than 9. 2 is less than 9. But all the elements which are on this curve are bound to be greater than 9, right? See, if this 17 is there, 17 is greater than 9. But you found an element like 2 here. You found an element like 2, which is what? Less than 9. That means this midpoint is coming after the dip. If it is coming after the dip, this is on the lower curve. And here you can see the midpoint is greater than 5. That means it is coming before the dip, right? See, let me give you one more example. Okay, so let's say 9, 10, 11, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the midpoint. And can you see 9, 10, 11 goes here, 1, 2, 3, 4, 5, 6, 7 goes here, and 2 lies somewhere here, right? So we can very easily detect. Here you can see if 17 is greater than 9, if this value 17 that you are trying to fetch, if this particular value is greater than 9, right, that means you are on the upper curve. If this value is less than 9, like this, then you are on the downward curve, because after 9, all of the elements greater than 9 are on the upper curve, right? All the elements lesser than 9 are on the lower curve. Now, you have the axis of 17, right? And you know whether it is on the upper curve or the lower curve. Now just think about it. If the target element doesn't lie in this range, you can see 9 is greater than 6, 17 is also greater than 6. That means 6 doesn't lie in this range, right? 6 doesn't lie in this range. That means you can discard this complete half and reduce yourself to this half. You can see if I discard all of this, this again becomes something like this, right? And similarly, if you come here, right, let's say you wanted to target of 6, midpoint is 2, right? Now, if the midpoint is 2 and you are coming here, you should compare these two sides, right? That whether 6 lies between 2 to 7 or not. If it does, then you can discard left half. Now, where I am coming from? I just told you one very simple fact, that binary search can be applied on two different search, like if you divide your search space into two halves, so that you can discard one half and take one half. Now, what is that property here? The property in this rotated sorted array is that if you divide your curve into two parts, if you divide your curve into two equal parts, one part will be completely sorted, one part will be unsorted. One part will be completely sorted, one part will be unsorted. One part will be completely sorted, one part will be unsorted. In this problem of rotated sorted array, once you divide your search space into two parts, you will see that either the left half is completely sorted and the right is unsorted, or the right part is completely sorted and the left is unsorted. That is the property that we are going to exploit. That's what I'm doing here. You cannot compare 6 here because this is not a sorted region, but this is a sorted region, right? From 9 to 17, we know that this is a sorted region. So if you can compare that, if 6 lies between 9 to 17 or not, it does not. That means if 6 doesn't lie in this range, 6 can lie in this range, and you again reduce yourself to a sorted rotated array, right? So you do low is equals to mid plus 1. Low comes here. Now you again calculate the mid. 4, 8, 4, 12 by 2, 6. Mid comes here. Now you compare mid with 19. It is less than 19. That means you are on the second half. Like you are on this curve, right? That means you are going to say that, let's compare the right part. Is 6 greater than 3 and less than 8? Yes, it is. So 6 is always going to lie in this part. You can discard all of this half. As simple as that, right? So you can see in every iteration, we are discarding one half. So low comes mid plus 1. Now 8 plus 7, 15 by 2 is 7 again. Here you can see this is equals to the target. You found the element, right? So that's what we want to exploit. That once you divide your array into two parts, one half will be always sorted, one half will be unsorted. The half that is sorted, we will compare our target in that half, that whether it lies in this sorted range or not. If it doesn't, then we move to the other side. And if it does, then we move to this side. Same thing here. You can see we divide into two halves. This is the sorted half. We check if 6 lies in this sorted half. Yes, 6 lies in this sorted half. So we discard the unsorted half, pick the sorted half. As simple as that. And again, you can see every time you are discarding n by 2 elements and you are picking n by 2 elements. Hence, you are applying binary search. So the time complexity of the solution becomes log of n, order of log of n. As simple as that. So let's just see the coding implementation for this problem and try to understand what we are actually willing to say here. Now let's try to code it. Okay. So let's take Java, right? Now, what I suggested, see, we are not going to do a lot of dry run or analysis for the problem. You should always try to think about the problem in terms of intuition, right? So let's see our basic intuition, okay? Initially, I'm going to define our low is equals to 0, high is equals to nums dot length minus 1. As simple as that, right? This is going to be our basic assumption, that this is the search space. Initially, the search space is the whole array, right? Once we are there, we'll say while low is less than equal to high. I'll apply the modified midpoint formula. Int mid is equals to low plus high minus low by 2. As simple as that. First of all, we'll directly compare that if nums of mid is equals to target, we return the mid, right? At least bare minimum we should do. If that's not the case, then we will say that check if target lies, first of all, check if mid lies in upper curve or lower curve. What is the upper curve? This is the upper curve. This is the upper curve. This one is the lower curve. So how do you check if you lie in the upper curve or not? You can say that if nums of mid is greater than or maybe equal to nums of low, that means you are in the upper curve, which is this case. Here you can see 17 was greater than or equal to 9, so it's in the upper curve. Else you are in the lower curve. If it is lesser, then you are in the lower curve. If you are in the upper curve, that is this one. If you are in the upper curve, right, that means your left half is always sorted. If you are in the lower curve, that means your right half is always sorted. So in the upper curve, your left half is always sorted. Left part always sorted. So compare there. Right, we will compare there that if target is greater than or equal to nums at left and target is less than or equal to nums at mid, although it's not going to be equal to nums at mid because we already had that condition above, right? That means target is in left part. If the target is in left part, you discard the right part by doing high is equals to mid minus 1. Discard right. Else it's not in the left part, target is in right, low is equals to mid plus 1. You can say discard left. And then similar thing we will do. If you're in the lower curve, right part is always sorted, right? So you'll compare if target is greater than nums at mid and target is less than or equal to nums at high. So that means target is in the right part. Target is in right. So you say low is equals to mid plus 1. You discard left. Else target is in left. High is equals to mid minus 1. Discard right. Okay, as simple as that. If you never return from this while loop, you return a minus 1. Let's see. Da-da-da. It cannot find the symbol. Okay, it should be low. We don't have a left, it's a low. Here we go. Let's try to submit. And boom. In one shot, we are able to submit the solution. Time complexity of the solution is order of log n. Right? You can see pretty easily we are able to submit the solution, and just based on the cases. And what property we exploited? We exploited the property that if you divide your curve into two parts, then one part is definitely sorted, other part is definitely unsorted. Based on that, we decided whether we are on the upper curve or we are on the lower curve. Based on that, we decided which part is sorted, which is not. Whatever part is sorted, we just compare our target there. If it is there, we go there. Otherwise, we go on the other side and just repeat the process. So you can see binary search just got applied on an unsorted array, right? So at any point of time, neither in your interview nor in your professional career, you should ever say that binary search can only be applied to a sorted array. It can be applied to an unsorted region as well. It can be applied to any search space where the search space can be divided into two parts where both of the parts differ based on some property. Now this is a new problem coming from LeetCode, problem number 153, find minimum in rotated sorted array. This problem is quite similar to the problem where we had to find a target element in a rotated sorted array that we just discussed in a different video, right? So if you already know about the problem, solution to this problem is going to be a simple cakewalk. Suppose an array of length n is sorted in ascending order and is rotated between 1 and n times, for example, something like this, right? Then it got rotated as 4, 5, 6, 7 and 0, 1, 2, right? It was rotated 4 times. If it was rotated 7 times, then you get the original array back. Notice that rotating the array this one time results in this. Given the sorted rotated array of unique elements, you can see all of the elements are always a unique element. You have to find the minimum. As simple as that. Now, considering that you already know about the problem that we discussed prior to this, that in a sorted rotated array, you need to find a particular element. You need to search for a particular element. If you already know about that problem, let's see how can you solve this. Now you can see in all of this problem, the minimum element is going to be where you get something like this, where the nature of the curve is something like this, because the minimum element is going to be the one which is having on the right side an element greater than it, and on the left side also the element is greater than it, right? This is going to be the minimum element, right? So again, if you go by the same approach, you can see nature of the curve remains as it is, right? Nature of the curve remains as it is. If mid lies here, right? If mid lies here, that means you can detect, right, that mid lies on the lower curve or the upper curve. If the mid lies on the lower curve, then your minimum element, you will check that, okay, this is on the lower curve. Your minimum element is always going to be on the left side. If mid lies on the upper curve, then you don't have to bother a lot. Your minimum always tend to be on the right side. Whenever you get the minimum, you also check that, okay, if the current element only is the minimum element or not. As simple as that. Because again, you can divide your search space into two parts. In one part, the array will be completely sorted. The other part, array will be unsorted. Exploiting that approach, if the mid goes on this part such that mid is on the lower curve, minimum element always exists on the lower curve. So if mid is on the lower curve, your minimum element is going to be on the left side of the mid. If mid is on the upper curve, you always know that minimum element is going to be on the right side of it. As simple as that. So let's take a bunch of examples given to us on LeetCode. Right.
So let's take an example from lead code. Okay. For example, you have something like 3 4 5 1 2. Okay. 3 4 5 1 2. Right. This is, let's say, the given array in front of you. Right. Now, if you calculate the mid, this is going to be the mid element. You can first of all detect that whether this mid is on the upper curve or the lower curve. You can check if the current element is greater than the element at the start, it's on the upper curve. So your smallest element is always going to be on the right side of the mid. Right. Now this is your search space. Now you can see your search space 1, 2 is sorted. Now for sorted search space, you have to be a bit careful as well. For example, if I give you a sorted search space like 1, 2, 3, 4, 5, you can see here you have a mid. Now, if you carefully see, what will you do? You will say that, okay, 3 is greater than 1. That means you're on the upper curve. So your minimum element will be on the right. But that's a problem. This array is not rotated. This is just the sorted array. So you have to always consider one particular factor, that whatever is your remaining search space, if your remaining search space is completely sorted, in that case, the starting element, like the leftmost element of your search space, is your answer, right? So here you can see, how can you detect whether your search space is sorted or not? If the starting element is lesser than the ending element, then your search space is sorted. You can see in these curves, the starting element is always greater than the ending element. Start is greater than the end. But in case if starting is lesser than the ending element, that means the whole search space is sorted, right? Then you want to get the leftmost element of the corresponding search space, right? So in this case as well, this is the search space and this is low, this is high. If the element at low is less than the element at high, then the answer is the element at low, right? You can keep a simple check. You can see on lead code as well, you have a similar test case, 11, 13, 15, 17. Now this whole search space is already sorted, so you don't need to bother a lot. Let's take this example as well, 4, 5, 6, 7, 0, 1, 2. Okay, 0, 1, 2, 3, 4, 5, 6. 6 plus 0 by 2 is 3. You got 7. 7 is on the upper curve. How do you know? First of all, this search space is not sorted. Then 7 is greater than 4. You are on the upper curve. So currently high is here, low is here. So you need to go mid plus 1. Now again, you got 0, 1, 2. Now the element at low is less than the element at high. That means this whole search space is sorted. The moment you got your search space as a sorted search space, in a sorted search space, always the first element is going to be your answer. As simple as that. So you can see in the worst case, you will be using binary search to reduce your search space from n to n by 2, n by 4 every time. So the time complexity of the algorithm becomes order of log n. Space complexity of the algorithm becomes order of 1. So now let's try to code the solution. First of all, what I'm going to do is I'll calculate the length, nums.length, and I'll prepare my search space from 0 to n minus 1, right? And then what I'm going to do is I'll put the loop. I'll calculate mid, low plus high minus low by 2. Then first of all, I'll check if the array is already sorted or not, or the search space is already sorted or not. So nums of low, if it is less than nums of, let's say, high, right, then you return nums of low. Otherwise, we'll check if mid is our answer or not. So in what cases mid will be answer? If the value of mid is less than mid minus 1, then mid is your answer, return mid. Right, for this you need to check mid minus 1 should be greater than or equal to 0. Mid minus 1 should be greater than or equal to 0 and this. Otherwise, if nums of mid is less than nums of mid plus 1, right? Or technically, let's see, if the nums of mid is less than nums of mid minus 1, that means you have an element which is lesser than the previous element. This is going to only happen in the case of mid, the smallest element. Otherwise, let's say the same condition to happen for if mid plus 1 is less than nums of mid, right? Then we should technically return nums of mid plus 1.
right? Simple cases, right? That is, if your next element is lesser than you, then your next element is your minimum most element. This mid plus 1 should be less than n. Otherwise, you are just going to check that if nums of low is less than nums of mid, then you are on the upper half. Your mid is going to be on the right side. So you'll say low is equals to mid plus 1, else high is equals to mid minus 1. At last, you can return minus 1, although we should always find a minimum. Okay, looks fine for this test case. Let's try one more test case. Looks fine for this one as well. Let's submit. Let's handle for the single length. If n is equals to 1, return nums of 0. Okay. Okay, we have one more case, 4, 5, 1, 2, 3. And our output is 1, expected is, output is 2, expected is 1. I believe somewhere in this check, it might be failing, right? So what I'll do is I'll say system.out.print mid, right? Let's see for this test case. Okay, you can see there is some problem here. So what do we say here is that if nums of, if mid minus 1 is greater than or equal to 0, that's good, right? So mid is 2, index 2. Oh, my bad. Here I am returning mid. So the solution is working fine, but we are returning mid. Instead, we have to return the element. So nums of mid, right? That was the problem. And you can see we have successfully submitted the solution. Fairly easy implementation altogether. We are here also checking whether we are on the upper curve or the lower curve. This condition is for the upper curve. This condition is for the lower curve. Then these two conditions are to just check whether the current element is mid or not. This is to check whether the array is already, the search space is already sorted or not. The time complexity of the algorithm becomes log n and the space complexity becomes order of 1. I hope the logic and the algorithm and the implementation of the problem is clear to everyone.